Welcome to lesson 2.6. This one will be a pretty long one, and there should be some new stuff here. So that's why I'm going to give you all of class time to work on the notes. I'm not just going to make this a homework assignment. You'll have some time to work on completing the notes in class, and then definitely jump in the breakout room if you have questions. All right, let's get started. First, look at the objectives. Pretty long list. Find the domains of rational functions. Use arrow notation. That should be a new concept. Identify vertical asymptotes and horizontal asymptotes. I think we have talked about them before in algebra. Now we're going to look at how to identify if a function has one before you even look at the graph, just from the function. We're going to talk about transformations with rational functions. So transformations that we've talked about in algebra 2 with quadratic functions, with absolute value functions, and so on, those same kind of transformations we're going to apply to rational functions. We're going to then graph those rational functions, identify slant asymptotes, so not just vertical or horizontal. So we'll take a look at that. And then eventually all this is leading to being able to solve applied problems involving rational functions. So that's a lot, but we'll get to them one by one. So first, let's define what a rational function is. Rational functions are quotients of polynomial functions. This means that rational functions can be expressed as a function divided by another function, where p and q are separate functions. Okay, q can't equal 0. Q of x can't equal 0 because you're dividing by it, right? So the domain of a rational function is a set of all real numbers except the x values that make the denominator 0. So again, it's all real numbers would be the domain, but we're going to focus on what's going to make the denominator 0 for the domain. So here's an example. F of x is equal to x squared minus 25 over x minus 5. If we're only being tasked to find the domain, I'm only focusing on the denominator. The denominator can't equal 0, so I'm going to set x minus 5 equal to 0, and I get x equals 5. So that means the domain is everything but 5. We can write that in two different notations. Set builder notation, you would say the domain of f is equal to, and then in brackets, you have x, the line, and then x can't equal 5. What that's telling you is all real numbers but 5. Interval notation shows the same thing. It's the interval from negative infinity up to 5, and then the interval from 5 to infinity. Notice how there's parentheses because we're not including the 5. Same question. Now the denominator is x squared minus 25. Again, if I'm being asked for the domain, I don't care about the numerator at all. It's all about the denominator. We set that equal to 0. This quadratic we can solve by taking square roots. So we're going to add 25 to both sides, take a square root. So that means x is equal to plus or minus 5. So those are the values that x cannot be in the domain of this function. Set builder notation would, again, brackets x line, and then x can equal negative 5 and x can equal 5. Interval notation, now you've got 3 separate intervals because you've got breaks at negative 5 and 5, right? Here's another one. Again, all I care about is the denominator, x plus 5 over x squared plus 25. We set x squared plus 25 equal to 0, and we find that x is equal to plus or minus 5i. Those are imaginary numbers, obviously, right? So that means there is no real number that x cannot be. So the domain for this function would be all real numbers. So no matter what notation you use, it's just going to be, well, here's the interval notation, which is just negative infinity to infinity. So that's what you would write for all real numbers. Next part of the objective is we're going to talk about arrow notation. So, I mean, you can read the chart, but this notation means x is approaching whatever the value of a is. So, in a real situation, it would be a number from the right, then it's from the left, could be approaching infinity or approaching negative infinity. So in this graph on the left side, you've got the f function approaching x from the right, approaching a from the right, and then it's also going to the right out to infinity. Over here, you've got it approaching a from the left, and then it's also going to infinity, negative infinity. So actually, that should be a negative sign there. Here you've got the function approaching a from the right, and then approaching infinity. That should actually be positive infinity. Here you've got x approaching a from the left, and x is also, the whole function is approaching negative infinity. So locating vertical asymptotes. Well, first of all, a vertical asymptote is a vertical line that your function will not touch. Um, so if you have a rational function in which p of x and q of x have no common factors, so it is simplified, and a is a zero of the denominator, so basically it's not part of your domain, then x equals a is a vertical asymptote of the graph of f. So if we look at a similar type of function, actually, we looked at this exact one in the previous example. We're first going to find out what are the parts, what is the domain of the function. So we look at the denominator, set that denominator equal to 0, x squared is equal to 1, so then x is going to equal plus or minus 1. So -1 and +1 are the limits on the domain. They are also going to be x equals those numbers are going to be the vertical asymptotes. So if I look at the graph, this is the graph of that function, but x equals -1 is a vertical line that this function will not touch, and x equals 1 is the same, is a vertical line that those functions will not touch. And there you can see those lines drawn. And the functions will, as they move, will forever get closer, but never actually touch. Another example, x squared plus 1. So if that's your denominator, there is no value of, if you set that equal to 0, right, you're going to get imaginary. If you set the denominator equal to 0, you're going to get imaginary solutions. So that means there are no values of x that would be a limit on the domain. So that means there are no vertical asymptotes. If you graph this one, this is what that one looks like, right? There is no vertical line that will not touch the function. Horizontal asymptotes are horizontal lines that the function, well, will either not touch in the examples left and center. On the right, it will cross through it, but then there will be a point at which that function will forever get closer to y equals b, but never actually touch it. So that is considered a horizontal asymptote as well. How can you determine if there is a horizontal asymptote? It's a little harder than finding a vertical asymptote. There's basically three categories that your rational function can fall under. So if you look at this, this is a complicated uh, example of a generic rational function. But if you notice, the exponent for the leading coefficient, for the leading term in the numerator is n, and the denominator is m. So you're looking at those two, you're basically looking at the degree of the numerator and denominator separately. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. If those degrees are the same, then you look at the leading coefficients and divide them. So in this case, whatever a sub n is, you divide it by a b sub m, and that's your horizontal asymptote, y equals that number. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. So first you have to figure out which category you fall in, and then depending on if you end up in the second one, then you have a little calculation to do. So in this case, in this example, the degree of The numerator is 2, the degree of the denominator is 2, so they're the same. So that means you fall into that second category, where you just then take the leading coefficients of the numerator and divide it by the leading coefficient of the denominator. So 9 divided by 3 is 3. So the horizontal asymptote of this function is y equals 3. And that's what this one looks like. If you were to draw the horizontal line there, y equals 3, this function will forever get close to it, but never actually touch it. Let's look at this one. So the degree of the numerator is 1, the degree of the denominator is 2. So the denominator has a greater degree. If that's the situation, the horizontal asymptote is y equals 0. And then this is what that looks like. So it does cross through, but as it extends out to positive infinity and as it extends out to negative infinity, it will never cross again. So like this part will never cross below, this part will never cross above the x-axis. And there's the y equals 0 as your asymptote. Third scenario, degree of the numerator is 3, degree of the denominator is 2. So the degree of the numerator is greater, and that means there is no horizontal asymptote. And this is what that function would look like if you were to graph this one specifically. Again, there is no horizontal line where the function approaches it in either direction. So we have two basic reciprocal functions. So one is 1 over x, the other is 1 over x squared. All of your rational functions are going to look like one or the other, with obviously some different characteristics, but they're going to fall into one of these two categories. 1 over x is considered an odd function, meaning if you substitute negative x in for x, you will just get the same, like you will get the opposite of then that the original function. So if I swap out x for negative x, it's just going to be 1 over negative x, or negative 1 over x, same thing. That's considered an odd function. And that has origin symmetry, meaning if you were to draw the line y equals negative x, your function is going to mirror over top of that line. 1 over x squared is considered an even function. If you substitute negative x in for x here, when you square negative x, you get x squared, just the same. So that means it's considered an even function. You just get back to what you started with, even if you swap in negative x. That has y-axis symmetry, meaning if you drew a line on the y-axis, your function would mirror across that line. And again, every one of your rational functions is going to be one or the other. We're going to now use transformations to graph a rational function. We're going to use the parent function of 1 over x to graph 1 over x plus 2 minus 1. So you're going to begin with 1 over x. And that's going to look like this, right? We know that it has a horizontal asymptote of y equals 0 because the degree of the numerator is less than the degree of the denominator. It has a vertical asymptote at x equals 0 because the denominator is x. If I set that equal to 0, you get x equals 0, right? And then they've determined two other points. So if I substitute negative 1 in for x, I get 1 over negative 1 over 1. And if I substitute 1 in for x, I get 1, 1, 1. So actually that should be negative 1 there, right? Because obviously substitute negative 1 in for x, there you get negative 1. Those are your 2 points. You got the horizontal asymptote. You got the vertical asymptote that we just talked about as well. All right, so that's the basic function 1 over x, but we're trying to graph 1 over x plus 2. All right, so at this point, if we identify then what is happening in the function, the plus 2 is inside the fraction, right? So that's going to move the function 2 to the left. So then the vertical asymptote is now at x equals negative 2. instead of x equals 0. We've shifted everything 2 to the left because of that plus 2. And then our 2-ordered pairs have also moved 2 to the left. The horizontal asymptote now is still at y equals 0. And the vertical asymptote has shifted over to x equals -2. Now we're going to focus on that -1, an operation happening outside the fraction there. We'll shift it up or down. That -1 is going to shift it down. All right. So we've moved both our points down 1. The horizontal asymptote has shifted down to y equals -1. The vertical asymptote that already moved to x equals -2 has not moved further. Okay. So strategy for graphing any rational function. The first is determine whether the graph of f has a certain type of symmetry. So you substitute -x in, and you determine if it has y-axis symmetry, meaning you get back what you started with, or if it has origin symmetry, meaning you have the opposite of what you started with. That's helpful to know. Then you're going to find the y-intercept, if there is one, by evaluating for f equals 0, meaning you just substitute 0 in and you get a point. You're going to then find the x-intercepts, if there are any, by solving the function when you set it equal to 0. Specifically the numerator, I apologize. And then you find any vertical asymptotes by solving the equation of the denominator equal to 0, which is what we've been doing. Fifth step, find the horizontal asymptote using our 3-category rule that we talked about. And then part 6 is plot at least one point between and beyond each x-intercept and vertical asymptote. You're going to try to find a point that's in between everything. Step 7, use all that information to graph the function between and beyond the vertical asymptotes. All right, so here you go. You're tasked with graphing f of x is equal to 3x minus 3 over x minus 2. First thing you're going to do is determine what type of symmetry you have. You do that by substituting -x in for x. When I do that, you end up with -3x minus 3 over -x minus 2. That is neither exactly what you started with or exactly the opposite of what you started with. So this one has no symmetry that we just looked at in the previous example. So there's no y-axis symmetry, no origin symmetry. So that's good to know moving forward. Step 2 is find the y-intercept. You just evaluate for f of 0. So you substitute 0 in for x, and you end up with 3 over 2. So now I know that 0, 3/2 is one of the points. Now we're going to find any x-intercepts. You get that by taking the numerator and setting it equal to 0. So we add 3, divide by 3, you get x equals 1. So now I know the y-intercept is at 3/2, or 1.5, and the x-intercept's at 1. Now we're going to find vertical asymptotes. You find the vertical asymptotes by setting the denominator equal to 0, and in that case we have x equals 2. So there's going to be a vertical asymptote at x equals 2. You find any horizontal asymptotes. The degree of the numerator is 1, the degree of the denominator is 1. So that means now we have to take since they're the same, you're in that middle category where you take the coefficients of the leading terms, so 3 and 1. So y equals 3 is a horizontal asymptote. Now you're going to plot points between and beyond each x-intercept and vertical asymptote. We know that the x-intercept is at 1. We know that the y-intercept's at 1.5. We know we had a vertical asymptote at x equals 2. So we're going to we're going to pick values of x to try. So we're going to pick x equals 1 because it's over here. We're going to pick x equals 1/2 because it's in between where we have some intercepts. We're going to pick x equals 3 halves, 1.5, because it's in between the intercept and the asymptote. And then we're going to pick x equals 2.5. They actually are picking 2.5 and 3. So again, you're just selecting points that are in between the information that you already found. So then now that you have those x values selected, you substitute them into the function and evaluate, and you get ordered pairs once you get the y's out of that evaluation. Now step 7 is graph the function with everything that we just did. So if you plot those points, here's what it's going to look like. Okay. Again, you've got the vertical asymptote going through there, the horizontal asymptote going through there. And here they are drawn on. Slant asymptotes. All right, so the graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator, specifically. So in general, if f of x is equal to p of x over q of x, p and q have no common factors, and the degree of p is 1 greater than the degree of q. You find the slant asymptote by dividing q of x into p of x. All right, let's take a look at what that is in action. So degree of the numerator is 2, the degree of the denominator is 1. In order to find the equation of the slant asymptote, you divide the numerator by the denominator. So if x minus 2 is the denominator, we're going to do synthetic division with 2 as my divisor. Right? Remember, you take the opposite of whatever you're doing to x in that situation. Coefficients of the numerator are 2, -5, and 7, respectively. So you drop the 2, multiply, you get the 4, add down, you get the -1. 2 times -1 is -2. 7 and -2 add down to 5. Okay? So that means it's a remainder of 5. You end up with 2x minus 1 plus 5 over x minus 2. So the equation of the slant asymptote is y equals 2x minus 1. So the whole graph of the function is shown there. The slant asymptote is that equation y equals 2x minus 1. That red line is the slant asymptote that is not touching either of those functions, or either of those two parts of the function. The vertical asymptote's at x equals 2 because the denominator is x minus 2. All right, now we have an application. All right, a company is planning to manufacture wheelchairs that are light, fast, and beautiful. The fixed monthly cost will be $500,000, and it will cost $400 to produce each chair. So that makes the function c of x is equal to the $500,000, that's the sunk cost, plus the $400 variable cost. All right, so write the average cost function of producing x wheelchairs. All right, so we're first going to find and interpret 1,000. So like if you were to produce 1,000 chairs, how much would it cost per chair? So it costs $400 per chair, right? Plus the $500,000 it costs to just set everything up. So we're just substituting 1,000 in for x. We're dividing by 1,000 because we're looking for the cost per chair. Basically, that $500,000 is then going to get split among the 1,000 chairs that you're making. And you end up with a $900 average cost per chair if you're making 1,000 chairs. What if you were going to make 10,000 chairs instead of 1,000 chairs? All right. So it's the same function. We're just substituting 10,000 in for x now. Ends up being $450. Why is it so much less? Because that $500,000 is the same no matter what. You're just splitting it up over the 10,000 chairs instead of the 1,000 chairs. So now your cost of making a chair is $450 as opposed to $900 because you're making more. This is why, huge companies have a cost advantage over smaller companies, right? They can produce things for less because they're making more of them. So think like Amazon. Well, I guess Amazon doesn't make anything; they just sell stuff. But um, think of whatever a big manufacturer as opposed to a small manufacturer, like maybe clothing, right? Think of like I don't know, Old Navy compared to some local clothes maker. Like an Old Navy can make clothes for a whole lot cheaper because they're making so much of it at once, right? And then if you make 100,000 shares, it's now at $5. Well, 405 total, but that's just $5 extra per share for that sunk cost. Okay. Um, so find the horizontal asymptote. If we were to graph this function, so they have the same degree, right? Because they're both just linear. So it'd be 400 over 1, which is y equals 400. So the horizontal asymptote is at y equals 400. That makes sense, right? Because you're never going to get the cost of a wheelchair below 400 because that's your variable cost per chair. Um, so you can, if you make like a million chairs, right, then it's only 50 cents per chair for that $500,000. But it's still something. So you're still adding something to that 400. So the cost of the wheelchair will never get to exactly $400. It will always be a little more, even if you make a million chairs or 10 million chairs. All right. So at this point, I have an exit ticket made for you that I want you to give a try. We'll go over that Tuesday first thing in class to try to have the notes and the exit ticket done by class time on Tuesday. And then we'll have a lot of time to work on the practice in this. If you have questions, again, while you were working on the notes, before you even try the exit ticket or before you try the practice, that's great to come into the breakout room to get some help with as well. All right, let me know if you have any other questions.